Hello everybody. Today we would like to talk a bit about the frequency drive technology, the different technologies, how they work, and the benefits from the different types of frequency drives. So I hope you will have some more knowledge around that when we have finalized. Okay. This is a frequency drive, or a drive, or a converter, or a frequency converter, or many names. Still the same, does the same. It converts the frequency from an input frequency to another frequency. There are different ways of doing this. In Rolls-Royce, we have for many years several hundreds of vessels with a technology that we call active front end. You have probably seen these three letters, AFE. So what is an AFE and what is not an AFE? Well, I hope you have seen the session where we talk about what is a frequency drive. Then you have some knowledge. Anyway, the frequency drive has two main components inside. It has a rectifier and it has an inverter. So the rectifier is rectifying the three-phase alternating current and making DC, plus and minus DC. The inverter is then making AC again, and at whatever frequency you would like it to be, dependent on which type of equipment you are controlling. So rectifier and inverter. You will in fact hear that some people say frequency converter about these internal units as well. So it may be a bit confusing, but if you keep in mind that we tend to use these words a bit different from person to person, you are aware of that, so you can maybe ask a question, what do you mean? So we call the overall cabinet a drive or a frequency drive or a frequency converter. And then we have the frequency converter units inside, the rectifier unit and the inverter unit. So active front end, what is that? That means that the front end is active. And I'm pointing at this end because this is the front end seen from the switchboard, from the grid. So from the grid you have 60 Hertz fixed frequency going into the frequency drive, and you have the rectifying unit as the front end unit. So active front end is then the active unit over here. To see the difference of an active front end to a passive front end, I have to make some drawings of that as well. Let's say we have here a something that is called 6 pulse, and here we have something called 12 pulse. We could add 18 pulse and 24 pulse as well, but I think when you see the logic between these two, you will easily understand the 18 and the 24 pulse solutions as well. So the 6 pulse solution has a rectifier as well, but this is a passive rectifier. It is a diode rectifier. It is based on passive components. The only thing these can do is rectify the 3-phase AC coming in, making plus and minus DC, and making again AC with an inverter unit. So the difference between the 6 pulse and the active front end is the rectifying unit mainly. So in this case we have an active unit that makes DC out of AC. By active components inside, I mean IGBT. You may have heard that expression as well. IGBT. It is diodes that are controllable, and you can push energy in both directions. This is more or less the same component as this one. More or less the same. The hardware is normally typically the same. And the inverter unit is the same for all solutions, because we need the active IGBTs to be able to produce AC. So if you have 12 pulse, 18 pulse, 24 pulse, 6 pulse AFE, this part is exactly the same. The inverter part, making AC. So the difference between active front end and the passive components is that we have diodes here, and we as well have diodes over here. The difference between 6 pulse and 12 pulse is that we have double set of diodes, a double set of a bridge of diodes, making DC, still passive components. So why do we do this? That's because the 6 pulse solution makes a lot of distortion on the voltage on the grid. The voltage on the grid should be like this, clean voltage. However, this diode passive bridge will make a lot of distortion on the voltage. You don't have to know much about this, but it's good to know that you will make distortions on the voltage, and the current coming from here will make these voltage drops on the alternating current. So the 6 pulse solution is the worst, because you have only one diode bridge and it's connected directly to the network. So this is making a lot of harmonic distortions. You may have heard that expression, harmonic distortion on the voltage. And that's why the industry have made 12 pulse solution, because on the 12 pulse solution we put a transformer in front of this. One single three-phase AC input, and we divide that input by 2 with an angle in between, so the passive rectifiers will not destroy the voltage as much as this one, because we divide the distortion on 2 different legs on the transformer. So the voltage from the network in this solution will not be as distorted as this one, maybe a bit less at least. So if we then add another leg, then we have 18 pulse, and then if we double up the transformers, then we have 24 pulse solution. So then you understand the 18 pulse and the 24 pulse solutions. So the first thing you see is, why do we in Rolls-Royce normally use an active front end? Well, we will not use a 6 pulse for a big propeller load, because we would destroy the voltage on board the vessel. So we wouldn't do that. So then we could introduce the transformer. The transformer would add weight and space into the vessel, and we can avoid the transformer by this solution, because the active rectifier is really keeping the voltage clean on the network. So we don't need the transformer. So that's the obvious reasons why we add and use an active front end instead of passive front end or pulse solutions. There is another big difference between this solution and those with pulse, and that is, in an active front end, the energy can flow, of course, in that direction, but as well in this direction. So the active front end is bidirectional. The power can flow seamlessly in both directions. With a pulse solution, where you have a passive rectifier, it's not possible for the energy, for the power, to pass through the rectifier. Because this is a passive unit, it will only rectify the AC to DC. So you can move your energy in that direction, but you cannot move energy backwards further than to the DC part. And that is the same for the 12 pulse as well. You can never go further back than you meet the diode, and then it's stopped. So you may have heard about brake resistors. Why do we use brake resistors? Well, if you have something here, maybe a winch, and this winch with the electric motor, you need to brake. You need to brake the energy, because when you're lowering the winch, you're producing energy backwards, and this motor becomes a generator, generating energy backwards into this inverter, and this inverter will then rectify because these two units are similar units. So this can as well rectify. And all your energy ends up in the DC bus, plus and minus. But it cannot travel further. So how can you then break this one? Well, then you need to connect brake resistors over this plus and minus. You need to control this so you can brake the winch controlled. So for all pulse solutions, 6 pulse, 12 pulse, you need to brake the energy coming back from whatever you have, if it is a propeller or a winch, anything. With the AFE that we have standardized on, we have 6 pulse and 12 pulse in our portfolio. We can deliver that as well. But due to our long experience with more than 200 vessels now sailing with megawatt frequency drives, we have gained so much experience, and we know exactly how we break the energy coming back from the propeller, from the winch, from whatever is out there. And we can break that energy by the load on the grid. So if you have a hotel load over here, you can break whatever over here. Well, you may say, can we break really a huge propeller, 5 megawatt? Can we break that propeller by load on the grid? Yes, we can. We can break a 5 megawatt propeller by just a small load on the grid. But if it is a small load, let's say if it is a light bulb, you can still break the big propeller, but it will take a long time. But you can still break it. So if you have time to break your propeller slowly, you can break it by a very low load on the network. It's a matter of just stabilizing how much energy you pass through based on how much load do you have on the grid. And this technology is what we utilize in our HSG solution. I talk about that in another session if you are interested. In the cube system with variable engine speed. In all these configurations, we utilize the fact that we can break the energy and we can go seamlessly in both directions through the active front end. So it's good to have this experience of the active front end. We can break a winch, we can break the propeller, we can have a generator working as a motor or a generator seamlessly in both directions. 6 pulse, typically in use for smaller fans and pumps on board a vessel. 12 pulse, you have seen that probably in many vessels for main propulsion, for tunnel thrusters and stuff like that. And for even bigger vessels, you may have seen 18 pulse and 24 pulse solutions for main propulsion to keep the distortion at an acceptable level. We don't need the transformer. We keep the voltage clean with the AFE solution. So the frequency drive itself may be a bit more expensive than this frequency drive and than this frequency drive. However, if you bring in the complete picture with the transformer, the installation, the termination, the cabling, and all that things you need to keep this system in a good way on board a vessel, then you're not far off with the active front end. And given all the other benefits, it's a good frequency drive. Nevertheless, we have these products as well, 18 pulse, 24 pulse, and in some applications it's wise to go in that direction. Okay, so please have a look at the other sessions as well, where we talk about the frequency drive, why we use it on board a vessel, and in the session where we look at the difference between a frequency drive and a starter. Okay, hope that was useful, and that you have a bit more information from this. Thank you.